Welcome, to our talk. So, it's great to be here. We fly all the way, from the Ivy Tower in, Illinois, Champaign, all the way, to here, meeting, all the folks who are actually saving the world in the real life. And so, what we're going to tell you about is the research we have been doing on addressing cross-system interaction failures. Basically, those failures that manifest through only the interaction between multiple systems, right? So, our goal clearly is to prevent systems from failing through the cracks. So I believe we are invited to this awesome conference because of the paper we published last year at USENIX. So here is Lydia presenting the paper very happily in our reading group before went to Rome to present the paper. So basically what we did is an in-depth analysis of 120 cross-system interaction failures, right, from systems we're all familiar with, such as Hadoop, Spark, Flink, HBase, so on and so forth. And we look into their root causes, their triggering conditions, their symptoms, and how they actually get fixed. And then learn tons of things. So my colleague Indy Gupta, who is also a co-author of the paper, apparently was very excited about the work. So he tweeted the paper, and he just referred to cross-system interactions as the dark matter of production incidents. And one data point he quoted from the paper is that among the 360 randomly sampled issues collected from the studied systems, we find 30 of them were actually cross-system, basically interaction failures, right? It's a very substantial amount of failures, and it's exciting enough for us to convince our grad students Xudong to work harder on it. And we even gave them a cool name called the CSI failures. Try to give you some feeling of the scene, the crime, scene investigation, where you have to connect the dots to be able to make sense of things. So apparently in this tweet actually raised a few discussions on Twitter. So here's Mark. Mark, probably many of you know him from his insightful tweets and blogs, sharing how to actually designing and operating large-scale distributed systems. So Mark basically commented that, hey, honestly, surprisingly, if this number is as low as 30%. So I just follow up with Mark. I say, hey, Mark, what does this number look like at AWS? Because we as academics, we don't really always have the luxury to look into real production data. It's kind of a luxury to us. By the way, if you actually try to looking for extremely smart and hardworking grad students to help you analyze the production incident data, or try to actually brainstorm how to actually make your site more reliable than now, there's a pile of super awesome grad students at Champaign. If you want to work with them, recruiting them, and also talk to us if you want. So Mark replied. He said, hey, I didn't really have hard data on it. But from my perspective, roughly, interaction issues are the majority, and not merely the plurality of production issues in large-scale distributed systems. So we even have more motivation to look into those problems. So the question is why there are so many cross-system interaction failures, right? What's going on? So the answer probably is obvious, because our production stack right now is mostly an orchestration of many interacting systems. Right, so our actually paper mostly look at this stack called so-called Hadoop stack, which actually started from this one project which is Apache Hadoop. And if you look at Apache Hadoop, it's a very interesting project in a way that it has a full stack of a number of interacting systems. Right, it has almost everything. It has a distributed file system HDFS. It has a resource manager YARN. It also have this computing framework called MapReduce. And if you are an old clock like me, who actually observe the evolution of Hadoop, you can see many of the other projects were actually a part of Hadoop, such as HBase, right? They were actually a part of Hadoop, and then later they becoming bigger, they spun off into an independent project. Summarizing the same story, it was actually led by my former grad student, Kaishen Chen. They were trying to do machine learning on top of Hadoop. And when they're becoming bigger, they spin off into a separate project. Right now, I think they're probably supporting, try to interfacing with Kubernetes. Of course, also supporting YARN. And if you're looking around, you will find there, the recent cloud systems or cloud native systems, they look much less like Hadoop, right? They look much more like Submarine and HBase. Right, they are actually each of the projects focus on one thing and try to do it well. right? And they are supposed to to interact with other systems in different ways, and they are supposed to be orchestrated into different stack used for different things. And if you think about it, they are all developed by independent teams and organizations. There's no unified interface. There's no unified format or APIs. And that probably explains why there are so many interaction issues. Right. So from the paper, we actually try to make a very obvious point, which is site reliability allow us to use this term because we are at SREcon. We think site reliability is determined not only by the reliability of individual systems, but also by the reliability of their interactions. And from the paper, what we learned is that interaction reliability is very hard, right? Part of the reason is there's very few formal descriptions about the cross-system interface, right? We actually look at many systems. We even work with some of the commercial cloud vendors. And all what I have seen is basically very simple open API spec, or earlier called the swag spec, which only basically describe or specify the constraints of API parameters, right? I would love to hear your practice offline about what are the specifications you have to make things more formal and easier to program to interface. So it is actually a word we don't even have something like POSIX, right? I hear everyone's complain about POSIX. It's incomplete. It actually don't specify certain critical properties, but we don't even have that, right? And then you can see those hilarious basically interaction failures like this one from the paper. In this case, Spark trying to read a file from HDFS, right? And it happened to be this file is big, so HDFS compress the file. And in the tradition of HDFS at that time, if you compress a file, you set this file.size to be -1, right? Because the size doesn't matter now. The size does not really reflect the true size of the file, right? It's obviously a bad practice to overload this field for different things, but probably it's fine earlier because everyone under the Hadoop project understand this tradition. But apparently Spark in this case don't really understand that. So it's actually try to do something good. It check the return file object and try to do an integrity check, right? And it finds how come file size is less than 0, and it must be this object is corrupted, so they fail the job, right? And the sad part of this failure is that if you look at each component in isolation, none of them did anything wrong, right? DFS does what it's supposed to do, and Spark does what's supposed to do. But when you combine them together, things break. And certainly, another fundamental challenge is to reason about error behaviors, right? I believe we all understand this very deeply, and you can see basically examples from the paper again. Here, Flink use basically Hadoop Yarn as a resource manager. In this case, they try to ask Yarn to allocate containers, right? And in this case, Yarn is a little bit slow because it's busy, so it processes the request a little bit slower. It takes time to allocate the resource. But unfortunately, Flink timeout and retry, very common practice. The sad part here is that in this case, Yarn take this retried request as a new request, right? And now, Yarn has to actually allocate 2 times more containers than what Flink was asked about, and it's even making Yarn slower. And Flink don't really are not patient enough. It retry basically hundreds of times, and essentially overload the Yarn. So you can see those sad examples in our data set. It's not even an uncommon one. So one of the challenge about reading about basically system interaction is that it's actually costly to think about multiple systems collectively, right? Part of the reason is we need new tools because many of our old tools only reason about one system. It cannot cross the system and the program boundaries, right? And even they do if you think about it, the search space grow exponentially if you combine multiple systems and try to reason about them together. And the problem is further magnified by many of the emerging cloud computing trends, right? Such as microservices, serverless, sky computing, hybrid cloud. Many terms you hear from conferences, and I believe many of you actually see this Death Star shape of basically microservice dependencies at Amazon.com back 16 years ago. It's amazing to think about the time. But if you think about all these kind of buzzwords, all what they are trying to do is they're either creating more interactions, or they make the interactions more dynamic and hard to reason, or they are trying to interact integrating things which are not supposed to interact, right? So the problem even becoming more emerging. And last year, from AWS reInvent, we learned the shape of microservices already grow from a Death Star to a galaxy. So if I have to put a summary of the paper, essentially, empirically, what we observe is that we find individual systems, they're becoming simpler and more fine-grained, thanks to serverless and microservice trend. So the good news is that each of them, they're becoming more friendly for testing, analysis, and verification. So there's hope there. But the bad news is that the challenge now, shifted, to the cross-system interactions, right? Because they're becoming more complex and error-prone. So new tools and practices are needed to tame them. And what we find is many of the traditional tools may not be sufficient anymore, right? Especially tools which only reason about controlling data flow within a program. It's very hard for them to cross the program boundary. So what can be done about it? There are a lot of things we can do, trying to address cross-system interactions, making sure they're reliable. But in this talk, I'm going to focus on this one thing Xudong and I have been working on in the past 5 years, which is testing and verification of systems with interactions, right? And I'm going to focus on these two components. For testing, what our goal is really try to find as many bugs as possible, especially bugs that manifest through interactions. And in terms of verification, Xudong has been working on building formally verified systems with guaranteed safety and liveness, right? And trying to building a bug-free system. So I'm not going to using Kubernetes as an example to make sure our discussion and techniques are concrete. And I believe it's a system everyone in the room are familiar with. I walk around the room these days, and I find so many talks about Kubernetes, so many products building around Kubernetes. So I don't think I need to explain what is Kubernetes too much. But from the very high level, you can view Kubernetes as a choreography of many controllers, right? All the controllers compose this huge system called Kubernetes. And we can see controllers, those building controllers, such as a scheduler, a stateful set controller, right? A deployment controller, and the garbage collectors. And they try to manage different resources in the system. And you can even see a huge number of custom controller which manage the applications, all kinds of applications running on Kubernetes, right? No matter it's a Zookeeper, it is a RabbitMQ, it is a Cassandra, right? And those controllers basically do auto-scaling, reconfiguration, all kinds of operations you need for managing those applications. And all the controllers essentially interacting with a strongly consistent data store called etcd in the bottom, right? And to be able to learn and change the system state, right? And the interaction is actually complicated because it actually goes through this layer called API servers to just share the load of the etcd. etcd is hard to scale. It's using a consensus protocol called Raft. And essentially, API servers cache some of the states represented as state object from etcd. Hopefully, just serve most of the read load. So, what are the different type of interactions each controller, in Kubernetes, are actually doing, right? So let's break it down. So the first type of interaction apparently is interaction between the controller and the etcd, right? Because the controller needs to learn the system state, it needs to change the system state. And as I mentioned, the interaction is go across the API server. So if you probably already familiar with Kubernetes, all the system state are represented as state object stored in etcd. And the second type of controller interaction is the interaction between the controller and its managed application, right? Because the controller has to reconfigure the application from time to time to basically match the desired state users basically declare. And the last type of interaction is the interaction between the controllers, because in Kubernetes architecture, it actually supposed to be multiple controllers coordinate to do some very big operations. And sometimes if you don't do it right, there are conflicts, there are interference. So next, we're going to break down these three types of interactions and show you how to reason about them and how to actually build tools to find the bugs inside. So Xudong is going to tell us about the first type of interaction between the controller and the system state, and some of the very cool tools he has been building.
OK, now let me use this Cassandra controller, which manages Cassandra deployments on top of Kubernetes, as an example to show you the interaction between controller and system state. So here in the current system state, the container deployment has two replicas, each running in one container and has one volume attached to it. And now let's say the user wants to downscale this container deployment from two replicas to one replica. And to achieve this desired state, the container controller needs to take multiple operations. It needs to first delete the container and then delete the attached volume. And this entire process is called reconciliation. During the process of reconciliation, unexpected failures and network disruptions can happen at any moment. So unreliable interactions lead to disasters. For example, the controller may crash in the middle between deleting the container and deleting the volume. And the network may be slow and unstable at any point. And in fact, there is indeed a bug in this container controller implementation that causes this problem. So if the container controller crashes after deleting the container, but before deleting the volume, like due to power outage or kernel panic, whatever reason, and after restart, the container controller starts to malfunction. It gets stuck in some error loop and will never be able to delete this volume. And failing to delete the volume further leads to resource leak and security issues. So this bug was detected by our tool, Sieve, and has been fixed by the developers. And note that this is just a really one example of how unreliable interaction causes failures. And there are many, many other different bugs with diverse and even more complex root causes causing other severe consequences. So to help developers detect those controller bugs before the controller gets deployed into production, we present Sieve, an automatic reliability testing tool for Kubernetes controllers. So the key idea of Sieve is to perturb the controller's interaction with the system state to trigger those interaction bugs. Sieve is easy to use. It does not require the developer to modify their controller to get tested. And more importantly, Sieve can reliably reproduce those detected bugs to help the developers diagnose the root cause. So to date, we have detected 46 series bugs in 10 popular Kubernetes controllers using Sieve. And we reported all those bugs to the developers, and 35 were confirmed, and 22 have been fixed. And those bugs lead to very severe consequences, including system outage, data loss, security issues, and so on. So Sieve is available on GitHub. So if you are using or building some controller and you worry about their reliability, test it with Sieve. So it is actually very challenging to test the interaction between the controller and the system state for several reasons. First, those bugs usually have very sophisticated triggering condition. Like the one I presented before, the bug is only triggered if the crash happens right between these two deletions. Second, those bugs usually have non-crashing symptom. Like in the previous example, the container deployment does not crash, but is in this incorrect state. So the testing tool has to correctly capture those symptoms. And finally, different controllers have very different implementation and diverse functionality since they need to manage different applications. So if we want the tool to be generally applicable to many different controllers, we cannot assume too much on their implementation. So the key idea of Sieve is to perturb the controller's interaction with the state. So to be more concrete, in Kubernetes, the system state is represented as a set of objects stored in etcd, and those objects are basically pod, config maps, default sets, whatever. And every object creation, update, or deletion advances the state. So the entire process of reconciliation can be represented as a sequence of states, starting from the initial state and ending at the desired state. And we term such a sequence of state called a reference run. The key here is that the interaction with the system state can be affected by many factors, including asynchrony, concurrency, failures, which are really common in any distributed system setting. So what Sieve does is that it runs the same workload in the reference run and produces this perturbed run by injecting some common and transient faults in the middle, which the controller is supposed to tolerate. And if the injected fault triggers some bug in the controller, we will end up having a different sequence of states in the perturbed run. Sieve's goal is to not only trigger the bug, but also reliably flag those buggy behavior to the developer. And to this end, Sieve uses differential oracles by comparing the two runs to detect liveness and safety violations without even knowing the semantic of the system. So how does this work? A common liveness property in controller is a controller should eventually achieve this desired state. And to check such a property, so basically compares the end states of the two runs to see if the controller in the perturbed run achieved the same end state with the reference run. And a typical safety property could be a controller should never delete any user data unless requested. And this can be checked by comparing the state updates between the two runs. In this way, Sieve can easily capture any inconsistency in terms of volume deletions. So Sieve exhaustively performs such perturbations with different patterns to systematically detect diverse types of bugs. Sieve has 3 major perturbation patterns, namely intermediate state, stealth state, and unobserved state. And for each perturbation pattern, Sieve exhaustively tests all the bug triggering perturbations to find as many bugs as possible. And to do so, Sieve needs to inject faults with different timings in different perturbed runs. And certainly, exhaustive testing can be very expensive. So to be efficient, Sieve also prunes out those ineffective perturbations, which are not going to lead to any bugs anyway. So now let me talk about more details about these 3 perturbation patterns. And the first one is the intermediate state pattern. So the key here is really that the interaction between the controller and the system state can actually fail in the middle, leaving the controller to handle some intermediate state after it restarts. So the reconciliation process usually takes multiple reconcile cycles. And in each reconcile cycle, the controller needs to issue multiple operations to update the state. Like here, the controller first creates some object which updates state from S1 to S2, and then the following update operation advances the state to S3. And similarly, the next reconcile cycle updates the state from S3 to S5. The problem here is that those reconcile cycles do not have any automaticity guarantee, unlike those database transactions. So if the controller crashes in the middle, it has to start over with those intermediate states, such as S2 and S4 here. So what Sieve does is that it crashes the controller in the middle of the reconcile cycles. Like if we crash the controller between this create and update, Sieve will force the controller to restart from S2, which is the intermediate state. And there's no reason that Sieve cannot reach the desired state starting from S2. The second pattern is called the stealth state pattern. And this pattern is really about the stillness in the interaction between the controller and the system state. And the stillness is caused by asynchronous caching, which is common in any distributed system. So for performance reasons, in Kubernetes, controllers usually interact with the system state in etcd through API server. And each API server maintains a local cache, which is a copy of the system state. And those cache the state is not guaranteed to be always updated with etcd. So here, the controller is connecting to API server 1, and it's reading from its local cache. So Sieve basically injects a delay to the API server 2. And while the system state evolves from S1 to S2, and then S3, you can find that the API server 2's state becomes stale. It stops at S1. And then Sieve reconnects the controller from API server 1 to API server 2. And after this reconnection, the old state S1 gets replayed. And seeing this old state S1 again, the controller should not do anything wrong. This stealth state pattern is actually a very notorious and very common failure pattern in Kubernetes. It has been widely discussed and has caused many real-world problems. And here is a long thread in the GitHub discussing these issues, which also inspired our work. And there's a more recent podcast discussing these issues in details. Feel free to check it out. The last pattern is called the unobserved state pattern. And this is about the observability gaps in the interaction. So when the controller interacts with the system state, the controller can choose to read the system state at any point. But there's no guarantee that the controller can see every version of the system state. So here, let's say the controller can observe S1, S2, but when the system state evolves to S3, Sieve injects a delay to the controller to prevent its read reaching the API server or etcd until the system state evolves again to S4 and then S5. And by doing so, in a perturbed run, the controller only observes a partial history of the system state changes. And this S3 is completely missed by the controller. And the controller should still work fine and reach the desired state, even if it misses 1 or 2 states in the middle. So to put everything together, CV is this reliability testing tool which focuses on the interaction between the controller and the system state. It requires the developers to provide some end-to-end test workloads as input. And for each workload, they will produce a reference run and generate a lot of test plans describing different perturbation patterns. And for each test plan, they produces a perturbed run and uses a differential oracle to compare the 2 runs to flag the bug to the developers. And CV is open source on GitHub, so try it out and test your controller with it.
All right, thanks, Xudong. So let me very briefly talk about the second type of interactions we discussed, which is the interaction between the controller and the application. Right? So the controller has to be able to reconfigure the managed application from time to time to match the desired state. And this is basically by no means easy because the controller has to respect all the semantics of the application. Right? Here I just show you one example. Here the application is Zookeeper. This is one paragraph of Zookeeper's manual about how to reconfigure it, right? You can already see it's super kind of tedious and complicated. Even basically the paragraph about adding one Zookeeper node takes 3 steps. Each step has a very complicated procedure. And if you mess it up, if you miss some steps, if you change the order, your controller is going to break the application badly. So the point I want to make is that we have to find a way to reason about end-to-end operation correctness if we really care about the controller and the application it manages, right? And here is a very interesting kind of position. The controller itself, the reliability probably does not even as matter as much the applications the reliability, right? Because applications are the ones you deploy and make money from. And one thing is that the unit testing practice of controllers may not actually be sufficient because those unit tests only making sure the controller itself running well. And sadly, what we find is many of the open source Kubernetes controllers, they actually primarily rely on unit tests for correctness. So to address the problem, to complement their practice, we built this tool called Acto, which is essentially a fully automatic push-button end-to-end testing tool. The key idea is to test the controller together with the managed applications, right? And check some of the end-to-end correctness properties. So we define 3 of them. First, the controller should always be able to reconcile the managed application to the desired state. And second, it should always be able to recover the application from some error state or undesired state. And lastly, it should be able to tolerate or defend against operation errors. And we actually applied this tool on. This is actually the old numbers, but actually we applied on more than 50 popular Kubernetes controllers these days and found hundreds of bugs. We found very few basically existing controllers can even satisfy all these correctness properties, especially the last one, right? The last one is probably too hard, and many of the bugs are confirmed and fixed by developers. And we actually asked a student who built a tool to come here to talk, but he want to go to KubeCon in Paris. He feel Paris is probably more fun. So the code base is there. If you want to using the tool to test your controller, let us know. We would love to help you to get things spinning. So let me just show you one example, of the type of bugs we find using Acto, right? Here is a very simple bug. We have a Zookeeper quorum, 3 nodes, and basically we use Acto to test it. And in some situations, basically Acto first downscale the Zookeeper cluster to 2, and then upscale it, and then you can find the bug. And the bug it's not that deep. It's actually basically in some code passes it failed to update the Zookeeper membership, and then you have a new pod talking to some old basically volumes, and then things breaking. And even worse, this controller has a liveness issue. It cannot actually take in any further scaling operations. So nothing looks good. So the basic idea technically is really try to basically build a tool to explore different transition of the application state, right? So basically we know that Kubernetes provide you a declarative interface where you can declare the state and basically making sure the controller reconcile the system from the current state to desired state. So the tool basically generating many different state declarations and try to keep the controller busy, just driving the systems into different state and then check whether it can do it. If it cannot do it, then probably there's a bug. And it not only generate a good state, it also generate bad state to test whether the controller is able to recover system from bad state and making progress. Right. It's also checking some of the level triggering principles each controller should be able to satisfy to see whether the controller can actually reconcile the system from different start state to the same desired state. So we have a lot of secret sources baking the tool to make the tool fully automatic and push button, including how to effectively generating different kinds of declarations which are comprehensively test those controllers, and also automated test oracles which can find bugs without human efforts. So the code is open source. Again, if you are interested, we would love to let you try out the tool. So we have been talking a lot about testing. We actually want to spend some time shifting to a very different kind of efforts called verification, right? To making sure there is no bug in the code, at least certain type of bugs. And if you think about the verification, we don't really have the luxury now to reason about one specific type of interactions and focus on that, finding bugs manifest through those. But we have to reason about all kinds of interactions if we want to build something which is bug-free. Right? So we have to be able to reason about all these interactions now, in this verification effort, including the third type of basically interaction we never talk about, which is the interactions between the controllers. So Xudong is going to tell us about the verification tool he has been building, which actually help us to reason about those interactions.
Okay. So the interactions between controllers further complicates the controller's reliability problem. So let's start from a simple example where we have a Zookeeper controller running in isolation. So this Zookeeper controller wants to first get some volume objects from the etcd, and then update this volume from version v1 to version v2. And because of etcd's multi-version concurrency control mechanism, the update request has to carry the current version number of the volume. So now let's look at some interaction scenario. We have a volume controller running concurrently, and this volume controller also wants to update this volume. And if the update happens before Zookeeper controller's update, the Zookeeper controller's update is going to fail. Because when the update happens, the version of the volume object has already changed from v1 to v2, so you will get a version conflict error. And in another example, let's say we have a garbage collector running concurrently. And if this volume happens to be an orphan object whose owner reference is not pointing to any existing object, and then this garbage collector is going to delete this volume. And in this case, the Zookeeper controller's update also fails because the volume no longer exists. And let's say if the delete happens a little bit later than update. Okay, good. This time the update succeeds. But the Zookeeper controller has to recreate this volume again since it gets deleted. So as you can see here, there are so many possible different interactions between controllers, and there are so many different controllers running concurrently in a cluster. So it's really, really hard for the developer to implement reliable controllers under all those kinds of interactions. So to help developers formally reason about the correctness of their controller implementation, we built Anvil, a framework to build formally verified controllers. So Anvil is implemented on top of another verification tool called Virus. So at a high level, it works in a way that it helps the developers to write controller implementation in Rust, and then write down the correctness specification of what the controller should do in some mathematical specification language, also similar to Rust. And then write machine checkable proof to prove that this controller implementation indeed satisfies this correctness specification. And with Anvil, we are able to build practical Kubernetes controllers. And we actually have already built 3 Kubernetes controllers using Anvil for managing Zookeeper, RabbitMQ, and Fluentbeat. And this verified controller actually achieve feature parity and competitive performance compared to the existing unverified controllers. So to help the developers reason about all kinds of interactions the controller faces, Anvil actually employs a formal model to describe different components in a Kubernetes cluster. To reason about the interactions between the controller and the system state, this model includes the API server and etcd, which serves and stores the system state. And to reason about the interaction between the controller and the managed application, this model has a part to describe the behavior of the managed application, which is customized by the developer since different controllers manage different applications. And to reason about the interactions between controllers, this model also specifies a built-in controller that interacts with the target controller, including garbage collector, stateful set controller, and so on. And of course, this model also describes asynchrony and failures, which is really common in any distributed system. Concrete example can be controller crash and network delay. So a key challenge in formally verifying a controller implementation is to first formally define the correctness property of the controller. So basically, what should the controller do? And to that end, we propose eventually stable reconciliation, ESR, which is a formal correctness specification for controllers. So ESR is a liveness property. It is generally applicable to diverse controllers and is powerful enough to preclude a broad range of bugs, including the bugs found by Sieve and Ecto. So ESR is written as a formula in temporal logic. And informally, this property basically means that if at some point the desired state stops changing, then the system state will eventually match this desired state and always match it from there. So to prove that a controller implementation indeed satisfies ESR, the key strategy here is to reason about one step of the controller at a time to show that the controller indeed makes steady progress towards the desired state in each step. So to be more concrete, let's say P here is a precondition for the controller to take one step. And Q is a post-condition for the controller to take one step, which basically means that what happened before or after the controller takes a step. And then the developers basically need to prove this formula written as P leads to Q. It means that if P is true, then eventually at some later point, Q also becomes true. Example could be if the volume exists with V1, then eventually the volume exists with V2, which means that the controller successfully updates this volume. And to prove this like a P leads to Q formula, developers need to apply an inference rule called WFN, which is from temporal logic of actions, also called TLA, invented by Leslie Lamport. And this WFN rule basically requires the developer to prove three facts to show this P leads to Q. The first thing is that if P is true, then after one step of the controller, Q becomes true. This basically means that the controller is able to make progress from P to Q. The second thing is, if P is true, then after one step of any component in this cluster, including the controller itself, either P or Q becomes true. This basically means that no other component in this cluster can prevent the controller from making progress. In other words, the controller is robust against all the interactions with other controllers. And finally, it requires this weak fairness assumption of the controller. It basically means that if the controller is able to take a step, and eventually the controller will actually take that step, it basically assumes that the network and the OS scheduler are fair. So this strategy allows the developer to construct a proof in a modular way that they can focus on each step at a time and then combine those steps together later. So suppose that you have proved the P leads to Q and Q leads to R. Because this leads to relation has transitivity, you can immediately get P leads to R. And indeed, developers can build up the leads to chain in this way to prove the controller eventually reaches the desired state, step by step, regardless of all possible interactions. And we are still actively developing MView and building more and more controllers using MView, and we hope we can release MView very soon.
All right, thanks, Xudong. We are closing. We actually designed a lot of closing slides, but in the end of the day, we just want to put one slide here. I hope to we just hope to share you with our vision towards a reliable cloud infrastructure. And you may say this is a dream, but we as academics, probably our job is to daydream in Ivy Towers, and hoping it's come true someday. So, but don't laugh at us. What we really trying to enable in the next few years is that first of all, we want to actually gradually replace existing Kubernetes controllers with formally verified controllers with proved safety and liveness. And meanwhile, we want to actually continue building testing tools, which is able to find bugs in existing Kubernetes controllers. Hopefully, try to find as many bugs as possible. We have some ideas about how to actually turn some of the testing tools into model checkers, which give us a bit more comprehensiveness. We're also thinking about how to actually specify certain interfaces, such as the very complicated human-written document interface into some specifications, so that we can check it in an automatic way. And hopefully, we have a we all have a much brighter cloud in the very near future. And I think that's all we have. And again, thank you for inviting us. It's really an honor to talk here.